Welcome to G Fun Facts Online. Today, we're talking about an echo from the quantum abyss. Scientists have detected a fleeting whisper from a realm of impossibly cold, frictionless existence. They've named it the Higgs echo, a name that calls to mind one of the most celebrated discoveries in physics. But this isn't an echo of the famous God particle that gives mass to our universe. This is its long-lost cousin, a mysterious entity that lives not in the vacuum of space, but in the heart of a bizarre and wonderful class of materials known as superconductors. This discovery is more than a curiosity. It's a key that could unlock a new generation of quantum technologies, from ultra-powerful computers to exquisitely sensitive sensors. It offers a glimpse into the hidden quantum pathways that govern matter, and a new tool to control them. This is a tale of two Higgs. One, the celebrity particle of the Standard Model. The other, a collective vibration in a superconductor. To understand the echo, we must first understand them both. The story starts not in a lab, but in the abstract world of theoretical physics in the 1960s. Physicists had a problem. Why do some particles, like the ones that make you and me, have mass, while others, like the photon, are massless? The Standard Model, our rulebook for the universe, was missing a page. In 1964, physicists, including Peter Higgs, proposed a radical idea, an invisible, all-pervading energy field, now called the Higgs field. Particles, they said, aren't inherently massive. They get mass by interacting with this field. The classic analogy is a cocktail party. Imagine the room is filled with people, representing the Higgs field. A famous scientist walks in. They're immediately mobbed, and their movement through the room is impeded. They've become massive due to their interaction with the crowd. An unknown person, however, can slip through unnoticed, remaining massless. The strength of a particle's interaction with the Higgs field determines its mass. The theory also predicted a particle associated with this field, a ripple, a quantum excitation. This became known as the Higgs boson. For nearly 50 years, it was the missing piece of the Standard Model. The hunt ended on July 4, 2012, when scientists at the Large Hadron Collider at CERN announced they'd found it. The discovery confirmed the Higgs field and completed the Standard Model, earning Higgs and his colleague François Englert a Nobel Prize. But that's not the end of the story. In a beautiful example of physics unifying power, the same mathematics used to describe the Higgs boson in the cosmos found a home in the microscopic world of superconductors. Here, we meet the second Higgs, the Higgs mode. This is not a fundamental particle. It's a collective excitation, a synchronized vibration of electrons inside a superconducting material. These vibrations are fluctuations in the strength of the superconducting state itself. The link is a concept called spontaneous symmetry breaking. In particle physics, the Higgs field breaks a fundamental symmetry, giving mass to other particles. In a superconductor, as it cools down, a similar symmetry breaking happens. This broken symmetry creates the superconducting state and gives rise to two types of collective excitations. One is the Higgs mode, the condensed matter analog of the Higgs boson. It represents oscillations in the strength of the superconductivity. So, while one Higgs is a fundamental particle giving mass to the universe, the other is a collective vibration of electrons in a material. The math is nearly identical, a testament to the deep connections in reality. It is this second, material-based Higgs that is at the heart of our mysterious echo. To understand that echo, we have to enter the wonderland of superconductivity. Discovered in 1911, superconductivity is a quantum state where certain materials, when cooled below a critical temperature, lose all electrical resistance. A current in a superconducting loop could flow forever. For decades, no one knew why. The answer came in 1957 with the Bardeen-Cooper-Schrieffer, or BCS theory. It describes an elegant dance of electrons and atomic vibrations. In a superconductor, electrons, which normally repel each other, form bound pairs called Cooper pairs. This pairing is mediated by vibrations in the material's crystal lattice. Imagine an electron moving through the lattice. Its negative charge pulls on the positive ions, creating a slight ripple, a region of enhanced positive charge. A moment later, a second electron is attracted to this positive ripple. Voila! A weak, indirect attraction is formed between the two electrons. This pairing is a profoundly quantum effect. Individual electrons are fermions, meaning no two can be in the same state. But a Cooper pair of two electrons acts like a boson, and bosons are social butterflies. They can all condense into the very same single quantum state. This collective, coherent state of all Cooper pairs is what allows for the frictionless flow of electricity. A key feature of this state is the superconducting gap. It's an energy barrier. It separates the low-energy ground state of the Cooper pairs from higher-energy excited states. The gap is the energy required to break a Cooper pair apart into two individual electrons. The size of this gap is a direct measure of how strong the superconducting state is. And this brings us back to the Higgs mode. Remember, the Higgs mode is an oscillation in the strength of the superconducting state. This means it's an oscillation in the size of the superconducting gap itself. The energy of this Higgs mode is typically twice the energy of the superconducting gap, which is precisely the energy needed to break a Cooper pair. This is a problem. It means the Higgs mode can easily decay into the very particles it's made from, making it incredibly short-lived and difficult to observe directly. This fleeting nature is what makes the discovery of its echo so extraordinary. Detecting this echo is a story of incredible experimental ingenuity. The team at the U.S. Department of Energy's Ames National Laboratory, led by physicist Jigang Wang, used a technique called terahertz multi-dimensional coherent spectroscopy. Think of it as a quantum version of a pump probe experiment, but on steroids. It uses a sequence of incredibly short pulses of terahertz radiation. First, two precisely timed and phase-locked terahertz pulses, let's call them A and B, hit the superconductor. These pulses are tuned to an energy that can excite the Higgs modes. By controlling the time delay between them, the researchers create a time grating, essentially imprinting a periodic pattern of Higgs coherence onto the material. Then, a third pulse, or rather a signal generated by the interaction of the first two pulses with the material, scatters off this time grating. This scattered signal is the Higgs echo, a faint, delayed signal that carries information about how the Higgs modes evolved over time. The experiment was done on a thin film of niobium, a conventional superconductor that's also used to build quantum computing circuits. It was cooled to 4 Kelvin, just below its superconducting transition temperature. What the researchers saw was remarkable. By analyzing the faint signals emitted by the niobium, they identified the unique signature of the Higgs echo. It had several strange characteristics. One was an asymmetric delay. In a normal echo, the signal appears at a time symmetric with the timing of the input pulses. The Higgs echo, however, was delayed, a consequence of the complex evolution of the superconductor under the influence of the strong terahertz pulses. Even more bizarre was the observation of negative time signals. Now, this doesn't mean information traveled back in time. It refers to signals that appeared even when the pulse supposed to trigger the echo arrived before the pulse that created the initial coherence. This paradoxical result is a direct consequence of the complex and harmonic coupling between the Higgs modes and the broken Cooper pairs. These unique signatures provided undeniable evidence for the Higgs echo, opening a new window into the complex world of non-equilibrium superconductivity. So what does this echo actually tell us? Why is it so important? The discovery is more than just confirming a theory. It's a powerful new tool. The echo is, in essence, a form of quantum memory. The superconductor remembers the information encoded by the initial terahertz pulses and replays it as the echo. As lead scientist Jigang Wang said, the Higgs echo can remember and reveal hidden quantum pathways within the material. By carefully designing the pulse sequences, researchers can not only see these hidden pathways, but also manipulate them. This opens up thrilling possibilities for encoding, storing, and retrieving quantum information. At the heart of this is quantum coherence, the ability of a quantum system to maintain a stable phase relationship between its states. Decoherence, the loss of this relationship, is the single biggest obstacle to building a functional quantum computer. The Higgs echo, by providing a way to control the coherence of a collective quantum state in a superconductor, could offer a new strategy to fight decoherence. This could have profound implications for quantum computing. Superconducting circuits are already a leading platform for building qubits. The fact that the Higgs echo was found in niobium, a material already used for this, means this new phenomenon could be integrated into existing quantum computing designs. We could imagine a new type of qubit based on the coherent states of Higgs modes, where information is encoded in their phase. The echo would then be the readout mechanism. Or, it could be used to create a quantum memory device. The Higgs echo could also lead to new quantum sensors, exploiting its sensitivity to the internal state of the superconductor to detect incredibly weak external fields. The discovery of the Higgs echo is just the beginning. It opens up a huge number of new research questions. One of the most exciting prospects is searching for Higgs echoes in unconventional superconductors, like the high-temperature cuprates. These materials are far more complex, and finding echoes in them could provide crucial insights into the still unsolved mystery of high-temperature superconductivity. Researchers will also refine their techniques, using more complex pulse sequences to gain even greater control over the quantum state of these materials. The long-term vision is to harness the Higgs echo for practical quantum technologies. The faint whisper from the quantum depths of a superconductor has told us a profound story about the hidden workings of our universe. It's a story of unexpected connections, of the beautiful unity that links the smallest particles to the collective behavior of matter. As we learn to listen more closely to these quantum echoes, we may find they hold the key to unlocking a new era of technology, an era where we can finally harness the full power of the quantum world. The echo is a reminder that even in the coldest, most silent corners of the universe, there are still new wonders to be discovered. Thanks for listening to G Fun Facts Online.